So today we are going to continue our discussion on this lower bound for universal relation on m bits composed with universal relation on n bits, and we are going to try and prove this sort of weak lower bound, which is m minus order square root m plus n minus order log m. This was the first lower bound proved by ERS in the 90s. So we were building up to this in the last lecture. So how do we start? We start with a protocol that is like more efficient than this. Like we assume that the communication complexity of this protocol is basically m minus order square root m plus an additional n minus order log m, and then we'll prove that this protocol would make an error. Using an adversarial strategy, we would craft a certain set of inputs, and then you use those inputs to find a path from the root to the leaf, such that on that path the protocol makes an error. But since we are studying this as the composition of two things, we divide the strategy into two stages. There's a first stage, which is the first m minus order square root m bits. So this is where we suppose that they're trying to solve the universal relation on m bits, and then second stage where they try to solve the universal relation on n bits. Okay. So and we do have like an important step in between, which is called cleanup, where we want to like say that okay, they could not have solved it in the first stage, and in fact they could not have learned a lot about this useful information about the second stage in the first stage by doing some cleanup on the set of inputs that we are keeping. Okay, so we had some guiding philosophies on how to design these stages. So in the first stage, one thing that we wanted to ensure is that okay, so this is the first m minus order square root m bits. This order is something like 4 or something. It's not too important. So one thing is that the players learn not too much information. So they learn less than this much amount of information about the column vectors, and they learn about this much amount of information about the matrix as well, about the matrix part of their input. Okay, so remember that in the universal relation composed with universal relation, the setup was that Alice and Bob get a matrix vector pair. So Alice gets XA and Bob gets YB. And in the promise version, the condition, like there were two things. There was the first promise that A is not equal to B, and there was a second promise that if for all I such that AI is not equal to BI, if so I in M, this implies that Xi, the corresponding rows are different. Okay, so we wanted to like craft a carefully chosen set of inputs and this carefully chosen transcript, so that even after m minus order square root m bits of communication, these two things happen. And then we want to do some kind of cleanup, which would enforce the following. So this is the cleanup stage. So in the cleanup stage, we want to say that they haven't quite yet solved the universal relation on m bits. More importantly, we can like somehow break the promise. We can keep the promise at the promise one at the end of first stage. So if you remember, the idea from the simple lower bound for just universal relation without any composition was to keep the symmetry as long as possible and break at the last very moment, or don't keep the promises until the very end. So at this point we want to like find some set of inputs so that we can keep promise one. Promise one, we can, okay, this might sound a bit vague to you, but it's not too important. The more important thing is that we said that okay, in the if our first stage, if we could implement our first stage, we know that in the matrix there are like about m minus square root m bits of information that the players have learned, so under some definition of what the players have learned. So there's like this is less than m bits, certainly less than m bits because it's m minus square root m bits. And then we want to say that if we choose a threshold tau, tau is a threshold, there are So we use this threshold to classify rows into two kind of rows. So one kind of row is called a revealed row. So a revealed row is where they know more than tau bits of information, and the other kind, any other kind of row is called unrevealed. So where they don't know so much information. So this is like where they know uh, less than tau bits of information. So maybe it's like greater than or equal to tau. So we want to say that, okay, so since they learned, so the total information here is uh, at most m bits, and in each unrevealed, in each revealed row there should be like at least tau bits of information. Number of revealed rows should be bounded by the total information, total info divided by the threshold. So this should be m divided by, so we would set our threshold tau to be square root m for convenience. So this would be something like square root m. So set tau equals to square root m, then we get that like this, at most square root m rows which are revealed. So we, at the end of this first stage, we want to clean up the input so that there are these two kinds of rows. One is a revealed row where they have learned quite a lot of information, and another is a set of rows which are called unrevealed row where they haven't learned too much information. So intuitively speaking, if in a revealed row, if they're allowed to solve the second stage. So in the second stage, we assume that they're trying to solve the row problem. They're trying to solve UN, or in fact, they're trying to find a difference in the corresponding rows of their matrix. Yeah. Hi. Oh, yeah. Oh, so the same issue. Thank you, Sasha. Is it gone? Yeah. Yeah. Cool. Thank you. Yeah. Also, please feel free to like stop me if there are any doubts or comments. Yes, so in these rows, if they're allowed to find a difference, then they have a certain advantage. They already know that, like in the first stage, we keep the matrices to the players to be the same. So they know that like these bits are same in both their matrices, X and Y. So if at all, if they're going to find a difference, it must be in this small portion, which is like at most m minus tau bits. So maybe they like, sorry, this is n minus tau bits. So it is possible that like they can do something better than communicating something like almost n bits of information. So we at the end, like what do we want to say is that like on revealed rows there is a certain advantage. So we want the players to be not able to solve the universal relation problem on these rows. So what do we do? So what we do is that in the corresponding, so we, in the cleanup stage, we are going to like set a set of vectors associated with a set of matrices, so that for every matrix that we are going to give in the second stage, every vector that the players Alice and Bob are get, or the a comma b, we're going to set them to be equal on revealed rows. So for every a and b that we will consider in the second stage, or for a good number of them that we are carefully choosing, this we'll set ai equal to bi for the revealed rows. So if you remember the promise 2, so the promise 2 said that the rows are guaranteed to be different only if ai is different from bi. So if you have a powerful adversary, it is possible that maybe if ai is set to be equal to bi, at the end of the second stage you can make these rows to be equal, and thus it is possible by a leap of faith that you can actually set these revealed rows to be the same for both the players, and then you can force them to solve the problem on the unrevealed rows. And on the unrevealed rows, intuition says that they have like, so this is a revealed row, right? And in the unrevealed rows, the intuition says that they know at most tau bits of information. So there are at least n minus tau bits of information that are not known to them. So by the universal relation kind of low bound, it seems plausible that they need to communicate another n minus tau bits. That's what we want to do. What we would end up showing. So we would like, so remember tau was square root m, so we will do something like n minus, so the second stage would be like n minus square root m bits long plus an additional log m to do some extra work. But we'll end up showing that whatever threshold that we chose in the cleanup stage to classify rows into revealed and unrevealed rows, in the second stage we would run about n minus tau bits. Okay, if they stop anywhere at n minus tau bits or before that in the second stage, they would make an error, and this would show that the protocol would make an error. Okay, so far this is all intuition, and uh, yeah, so I did not define what is information here. I did not define um, yeah, I did not define how it is measured with respect to Alice or Bob. Are we measuring it separately? But at least I hope the intuition is clear to you. uh, one more thing before we continue along is that, so we I said, like, as an adversary, it's important that we set these revealed rows the bits corresponding to the revealed rows AI and BI to be the same. So there is another small intuitive calculation that you can do to make sure that this would not reveal all the information about the vectors A and B. So remember, at the end of first stage, uh, the information revealed on the columns is something like what? This is less than m minus, let's say, 4 square root m. And then what we are going to do is, like, for every revealed row, so maybe this is a revealed row, there's a lot of information leaked here, we are going to set this bit to be equal for both Alice and Bob. Maybe in the first stage they did not speak about this bit, so maybe this bit was not accounted for in the m minus 4 square root m. So we are revealing an additional bit of information on the column vectors, right? So it's possible that for every revealed row that we fix, we reveal an extra bit of information on the vectors. So at the end of cleanup, what could happen is that the amount of information in the columns could go from m minus 4 square root m to what? M minus 4 square root m to an additional square root m. So this is still less than m. So this is still strictly less than m, and this would be useful to, like, keep the promise at the end of the cleanup. So we want to keep promise one at the end of the cleanup, but yeah. So after the cleanup, what do we have? We have these revealed rows and unrevealed rows. And revealed rows, the column in the corresponding column vectors AI and BI are said to be the same, so that they cannot solve the second stage on a revealed row. And we know that even after fixing all the revealed rows, we have some bits of uncertainty in the column vectors. So it's not that all the column vectors that are remaining are just the same A and B. Okay, so yeah, how do we implement this intuition? So we have to uh, define a set of inputs that we care about in the first stage, and then we have to show that the intuitive claim that we made about the first stage is true, that we reveal this much amount of information on the column vectors and this much about the matrices. And we saw this already in the last lecture. How do we do that? So if you remember, so this is the first stage. So this is like the first m minus 4 square root m bits or something. So for starting with the root, so like if we have an intermediate node we'll build this transcript, we'll find this, trace this one path from root to one of the nodes at this level, and at an intermediate node pi, we would have kept an interesting set of inputs s pi, which is all a set of matrix vector pairs which can be given to both Alice and Bob, such that if you run, so this is this protocol pi, so if you run protocol pi for these many bits, so you give xa to Alice and xa to Bob, it reaches pi. So if you run this protocol, the messages would be in correspondence with the label of this path. Okay, and note that this set of inputs is is a set of inputs where they cannot solve the universal relation, right? Because there's like, if they have to solve the composition of a universal relation, Alice and Bob have to find a bit of like an index in the matrix, so that the corresponding entries for Alice and Bob are different. But here there are no differences in the matrices or the vectors, so they can't really solve the problem. In the non-promise version, maybe they can say pub, because like no promise is kept, but they really cannot find any difference either in the column vector or in the matrix. So we really are kind of stalling progress as much as possible, right? Okay, so and then we came up with this way to visualize this set, so that we can choose the next bit, making sure that in we'll go from S pi to one of its children, S pi 0 or S pi 1. So the situation is like, maybe internally it looks like this. So here is pi, it has two children. So here, like, maybe this is Alice's node, and Alice sends 0, and then here it is like Alice sends 1. So there are like two, so we call this pi 0, and let's call this pi 1. So we would choose like, and you can define correspondingly S pi 0 and S pi 1, and we showed that S pi 0 is nothing but uh, S pi intersection x0. So basically what happens is here is that if, okay, so it's basically the like the set of inputs that it's intersected with the set of inputs of Alice that are consistent with the message 0. So yeah, so what happens here is that, okay, if you denote the rectangle of inputs here by, let's call it U cross V, it's not really neat because yeah, I can't think of a denotation. So what is U? U is a set of inputs of Alice. So these are matrices x comma a, right? It's some set of matrices and vectors x comma a, and this is set of inputs of Bob. Let's call it y comma b. So this is the rectangle associated with this node. What happens is that when Alice speaks the bit 0, she partitions this set U into two parts. She partitions it into, so U gets partitioned into U0 and U1. So the rectangle here would be U0 cross V. The set of inputs of Bob doesn't change, and here also it set of inputs of Bob wouldn't change. So this is U1 cross V, and then we know that U0 and U1 form a partition of U. So we know that what is S pi 0? S pi 0 is just S pi intersection U0, and S pi 1 is just S pi intersection U1. Okay, so we know that like at least, okay, so this is the scenario here. This is what happens, and we want to choose either S pi 0 or S pi 1 or a subset of it. So maybe we would not keep all of S pi 0 or all of S pi 1, but we want to choose a direction, and to say either we want to choose a transcript on the left or the right, so that these two guarantees are kept. First, it reveals like the transcript and the set of inputs that we choose reveals at most one more bit of information on the matrices and one more bit of information on the column vectors. So how do we do that? How do we choose it? It was not so simple as like choosing like so in the simple universal relation, what we did is that, so we choose next bit B from 0 1 to B. So for this was the lower bound for universal relation on m bits. If it was just that, what did we do? We did this S pi B to be the heavier of the twos, or something that is at least as heavy as S pi by 2. So this was a simple thing to do in the simple universal relation, but we are in the composition, so we have to think about information that goes into the matrix and information that goes into the vectors. So we kind of intuitively said that if a set gets halved, it's like in revealing one bit of information. So here the problem is that we don't know where this one bit goes. Maybe it goes into the matrix, maybe it goes into the column, maybe it goes in a sound of like very complicated way. So maybe some partial information goes into the matrix and some partial information goes into the vector, so on and so forth. So this is like kind of non-trivial to address. So what we do is like we sacrifice it and carefully choose a subset that so that the number of matrices that we have in S pi gets halved at most, and the number of corresponding vectors also get halved at most. So how did we do that? So we started with, so this is not what we're going to do. We will visualize SPy as following. We will visualize it as a tree where there's an empty node, let's root, but let's call it E, and the children of this node are all the matrices x1 x2, let's say xl, that appear. So these are all x's, so these are all nodes that belong to SPy. So what do I mean by that? So this sum xi is in here if there exists some a such that xi comma a is in SPy. You get it, right? So these are all, so you look at this set SPy, it's a bunch of, it's a collection of tuples. So in each tuple you have a matrix and a vector. So you first collect all the matrices that appear in the set SPy and label the first layer of this tree with those matrices. So these are all matrices. So we are just viewing this tuple as some kind of stage thing, and for every xi we have all the children of this node xi are all a's, such that, I don't know, ap such that, so for example this node represents that, so this node represents that x1 comma a2 is in the set SPy. So remember, like we have two trees now, right? There's one is a protocol tree where we had the node pi and it has two children pi 0 and pi 1. This tree is not that. This tree is like, so at every node we had this carefully chosen set of inputs SPy. So which, oh okay, so by the way, because we are going to discard some set of inputs, this need not be all x comma a that can be given to the players. So this is a small mistake here. So this is a carefully chosen subset of this set. So it's a, so at every node we have some set of matrix vector pairs which can be given to both the players. We choose this set carefully and we can visualize this set as following, as this is this tree. So now we have to choose the SPy, so we have to like choose a next bit and a corresponding set SPy p, so that we reveal one bit of information the column vectors and one bit of information the matrices. So what do we do? So when, let's say it's Alice speaking, so what is Alice going to do? So on some xa pairs she might send 0, and on some xa pairs she might send 1. So she in fact ends up labeling this tree with zeros and ones. So maybe on this pair Alice sends 0. So we would label this with 0. So and maybe this is also 0, maybe this is 1, this is 0, this is 0, and so on and so forth. Okay, so we have a similar thing. So here also we have like a bunch of nodes and bunch of vectors associated with this. Maybe we don't have a3, maybe we don't have a2 there, maybe we have a4, I don't know, a5, and the situation here is like, it's like 1 1 1 0. So the next bit that Alice sends labels the leaves of this tree into like two labels. So 0 if on that matrix, so if she has this input she'll send 0, and on x1 a1 Alice sends 0, and x1 ap maybe she sends 1. So we get a complete labeling of the leaves of this tree. So now we want to propagate this labeling onto the matrix part on the next level. So what are we going to do? So we label the matrix as the following. So the label of this matrix is going to be the majority label that you see on its children. So for example, what is the label going to be in this particular example? All but one child has label 0, so the majority label is 0, so this matrix gets the label 0. But for example, if you look at this matrix, majority of its children have label 1 and it gets label 1. So whatever, so here's an simple fact about this labeling. So if you have, if a matrix is labeled 1, then at least half of its children would be 1, right? Because there are only 2 labelings, so majority is 1, means that there's at least half the children who are labeled 1. And now we want to propagate this label one more level up. So the communication only labels the leaves, and we took this majority vote and took these labels to the matrix level, and then we want to think of like a single label for all the matrices. So we take the label of this empty root to be the majority vote among the labels of the matrices. So if most of the matrices are labeled 0, so this root would get 0, or if majority of them are labeled 1, it will get 1. So what are we going to do? How are we going to choose the next bit? So we wanted to ensure two things, right? So in the next bit thing, we wanted 2 guarantees. So number of matrices at most halves, and number of vectors at most halves. Okay, so what are we going to do? So the obvious strategy is the following. So we look at the label of the root. Let's say it's 0. So we first delete all matrix vector pairs which are labeled 1. So for example, I delete all these matrices. So all of them are deleted. I don't know if this color scheme is good, but if you have any problem seeing this, please let me know. Okay. So if the majority of the matrices have label 0, we delete all the matrices which have label 1. Also, we delete all the vectors that are associated with that matrix. So this is kind of an overkill. Like, okay, but we can do that. Why not? We are the adversary. We are choosing our set of inputs. And now, like, every matrix that survives must have label 0. But it's clear that, okay, we can't take all of those matrices, right? So for example, like, yeah. So now, so if you look at the 2 set of inputs that are here, so there is like x1 a2 on x1 a2. So at node pi, if you had x1 a2, Alice would send 0. So Alice sends this one here. And if at node pi, if you had x1 ap, she would send it to the right child. So you have to choose, like, you can only choose one of them. So because we are choosing the 0 side, what we're going to do is, like, we are going to clean up the leaves of the surviving matrices. So for every matrix that had the label as the root, so every 0 matrix, uh, we will delete all the vectors whose label is 1. Okay, so this is sort of a 2-stage pruning. So we first deleted all the matrices whose label did not match the label of the root, and then we delete all the so when we delete those matrices, we kill all of its children as well, and in the surviving matrices we kill off all the children whose label is different from the label of the matrix. So what do we end up having? How many matrices do we have left? We have killed at most half the matrices, right? So this part is done. So this we are good. Because we chose the majority label for the root. And how many, so for the surviving matrices, so this kind of conditional information, if you have seen what that is, but otherwise just intuitive think about, like, okay, you're measuring the amount of information on the column vectors conditioned on the, like, after giving the matrix part of the input to both the players. So for the surviving matrices, how many children did we lose? How many vectors did we lose? At most half, right? Because so if the label of x1 was 0, at least half of its children were labeled 0. Okay, so this is how we choose the next bit. So in this case, we would go from s pi to, so we visualized s pi as this tree, and then we go from s pi to s pi 0, where s pi 0 is this carefully chosen set. Yeah. Okay, so now it is clear that this is not the set of all. This is where I said it's important that we are not giving all possible XA pairs at this node to S pi. We are only choosing a subset of them. So for example here, for example, if you look at the input XLA5, so this input pair, on this input Alice says 0, so it is in pi 0, but it could have been given to S pi 0, but we are not going to choose it. So we are only choosing a subset of inputs that can be given to both the players. Okay, but but we got what we wanted. We revealed at most 1 bit of information for Alice and then 1 bit of information for Y. Yeah. Okay. So at the end of first stage, after m minus square root m bits, so at end of first stage, we have some transcript, let's call it pi, okay, such that the set S pi, which is some carefully chosen subset of all inputs XA that can be given to both Alice and Bob, such that XA would reach this node pi. And what do we have? What are the guarantees that we have? So let's denote X pi to be all the set of matrices X such that X appears in this S pi as a tuple. So remember, S pi is a tuple of things. One is the first coordinate is a matrix and the second coordinate is a vector. So this is all X such that there exists in A, such that X comma A is an S pi. So what do we know? So for the cardinality of X pi is at least cardinality of X root divided by 2 to the length of pi. So this was, how many bits did we communicate for? That was something like m minus 4 square root m. So this is at least 2 to the m minus 4 square root m. So we have these many matrices. Okay, and in the X root, how many matrices were there? Initially, like any matrix could be given to both Alice and Bob. So it's the total number of possible m by n matrices, and that's exactly 2 to the mn. So this is 2 to the mn divided by this quantity. So this tells us that like we have revealed at most something like m minus 4 square root m bits of information. Okay, and we have one more fact. So let's define Ax as the set of all vectors A that can be given with a particular, so this is some, so this is careful, so this is some X that belongs to X pi. So for every matrix X in X pi, we want to denote the set of vectors that are associated with that particular matrix as this set. So this is not curly X, this is a particular m by n matrix. So given a particular m by n matrix from this set X pi of all the matrices, so Ax is all the vectors that can be given with this particular matrix. So this is all XA such that this is in S pi. So if you remember the tree picture, this is X. So here this set is A of X1. Okay. So this set of vectors that are associated with X1 is curly A X1, and the set of matrices on this layer is X pi. Okay, just some notation. So what is the other condition? So for all X in X pi, we know that this curly AX, the cardinality of this is at least cardinality, so the curly A root, so because in each step what did we do, we ensured that the number of matrices at most halves and the number of vectors at most halves. So this also has at most halved each time for every bit of a communication. So the number of bits of communication we set in the first stage was m minus 4 square root m. So this is something like this. So what is A root? A root is at the beginning of the protocol, they have no information on what the vectors have. So the cardinality of A root is all the set of possible m bit vectors, which is exactly 2 to the m divided by 2 to the m minus 4. So this quantity is 2 to the m, right, by similar. So we know that there are quite a lot of matrices, and for every matrix there are quite a lot of A's that are left. Okay, so now we would do the cleanup. So this is the we finish first stage, and this is the set of inputs that we have. So that we have quite a lot of matrices, and for every matrix that we are considering at this point, there are quite a lot of vectors that can be given to both the players. Yeah, and how much, that is controlled by this number, but yeah, it will become important in the cleanup. So what are we going to do in the cleanup? Remember that our main task is to classify the rows of the matrix into revealed and non-revealed rows. So we need some kind of measure of information that, so if you think about it, so far we have been considering this matrix as a single object, and we have been thinking of the set of matrices, and we said that the set of matrices haven't shrunk much. So the set of matrices only like a half at most m minus 4 square root m times, so the at most m minus 4 square root m bits of information revealed on this matrix. But then we wanted to use this fact to say that this information must be sort of spread out. Yeah, it cannot be that so we know, so what do we mean by that? We want to do some kind of averaging to say that, so this set x pi, we know that the total amount of information that is revealed is at most m minus 4 square root m. We want to say that it cannot be that in every row you have like quite a lot of information. We want to say that if there are these bits of information, it should be spread out. But this is not so simple. So we need like a careful definition of how we measure information across the rows. So far we've been thinking of it as like sets, and then we have been only looking at cardinality of how many matrices are there, but we have not been distinguishing between the rows based on how much information there has been. And we wanted this kind of fact to say that we wanted this property from the definition of information that if for any threshold tau number of revealed rows, so these are the rows where there are more than tau bits of information, is at most total info on x pi divided by tau. So you want to say that, okay, it cannot be that every row is really revealed. These m minus 4 square root m bits of information have to be spread across the rows. But so maybe one thing you can think about is like in the simple model is like, do they exactly know a bit of the metrics or things like that? So let's consider the following set of matrices x pi, where like we had some kind of naive protocol where Alice said that the first message of Alice to Bob in the first stage maybe was that, okay, the parity of my first column is, so Alice speaks, since that parity of the set of inputs that she is looking at, uh, so she sends some message. So what I'm trying to do is like I'm trying to construct a set x pi where it might not be it might not be simple to distinguish between the rows. Okay, like it's not so trivial to say that information has to be spread out. So let's consider this set x pi. I don't know how they constructed this. They had some kind of clever protocol in the first stage which said that, okay, so in the first column, so Alice and Bob know that the set of inputs that they are looking at in the first column, for all, so the information that they know, that for all x and x pi, parity of the first column is parity of x1. Okay, maybe I should not use x1 for columns. So x subscript 1 is the row x1, and x superscript 1, let's call it x1, column x1 is 1. So if they are indeed looking at if we constructed a set xpi for this protocol, and somehow based on the messages for Alice and Bob, it had this additional property that for every x1 that is in x, for every x that is in xpi, the parity of the first column is 1. So it seems like, okay, where do you attribute this parity to? It seems like for every, so you could say that, okay, I know the value of this row, this bit of this row, because if you give me everything else in these columns, then I can figure this out. So it's not that, but I can say that about this row also. Like, so there's only one bit of information, but it's spread across the rows, right? But we need a non-trivial definition so that we can somehow attribute it to one of the rows. It's not clear, like it seems like, where do you attribute this information to? So this information is not particular to one row, right? It's saying that the parity of the first column should be totaling to 0. So if I give you everything but a specific row, it is like that the so if it seems like, okay, so if I give you everything but this row, then you know what is like, and I tell you these values here, then you know what is the value here. So maybe if the values here add up to parity 1, and then I know the parity of the entire column is 1, so then by the virtue of that I know that this bit has to be 0. Or if the parity of these things are like 0, then this has to be 1. So but then it's not clear, right? I mean, it's but I could have said that about like this row as well. So maybe if you give me everything but this row, then one of the bits of this row is fixed. So yeah, so we have to like somehow attribute this kind of complicated information that is like conditionally, so this is like only one bit of information, but it's like spread across. So we have to use some kind of conditional information so that we can somehow attribute it to one of the rows. So here in this particular example, all the rows are good candidates, and we cannot say that it's one particular row that is carrying that information. Yeah. So what is, so the definition of information that we are going to use is something very combinatorial. It's from the original paper of EIRS. They call this predictability, but I want to present this by a different name. It's like sort of similar. So yeah, how do we, so what is this measure of information? So before we define what is our goal, we want to say, come up with a measure of information for the set xpi. So these are the set of matrices. So one in the main one thing is that we want to step, so we know that, okay, so first thing, like since xpi is at least x by, sorry, x root by 2 to the m minus square root m, the total amount of information info is on xpi is strictly less than m minus square root m. And then the second part is more important. We want to say that it's spread across the rows, right? Number of revealed rows is at most m minus, so at most this m minus whatever square root m divided by tau. So I think, yeah, this should be a 4 square root m here, but yeah, some order square root m. Okay, we'll fix those things later. So these are the two properties that we want. So how do we measure? So first thing is to like, okay, so we want to measure the spread of information among the rows. So you want to measure how much information is there in a row. So this is the definition. Predictability. So this is given any set X, which is a subset of all m by n matrices. So 0 1 to the m by n is all binary matrices of m rows and n columns. So x pi is in fact such a set, right? So given X is then, and a row I in M. So given such a row, so the way we look at the information that the players know about this row is as follows. So we think of this set X as a binary graph. So how do we do that? So let me introduce some notation. So let me define X minus I to be the projection of the set of matrices X onto all the rows but the ith row. So what is this? So this is all set X minus I such that X is in X. So this didn't exactly define this notation because I introduced something else. So for any matrix X which is a matrix in, so it's this element of 0 1 cross m by n. So given any matrix X and a row I, X minus I is this partial matrix. So this is the matrix I. So sorry, this is the matrix X, and let's say this is the row I. X minus I is this partial matrix where I delete this row and keep all the other rows. So X minus I is an element of 0 1 to the m minus 1 cross n. So this is a matrix with m minus 1 rows and n columns. Okay. So there are any questions about this definition? So what are we doing? So as a set, this we take a matrix X, we delete its ith row, we get a matrix with one less number of rows, and that's the, like that partial matrix is what X minus I is. Okay. Yeah. So for example, if we had, like, I don't know, the set of matrices to be, let's say 0 0 1 1 0 1 0 0 1 0 1 1 0 0 1 0 1 0. Let's say this is our set X. Okay, what is X minus 3 here? So this will be all the partial matrices obtained by removing the third row in set of matrices in X. So what happens? So these are all, so from this one we would get 0 0 1 1. So we are removing the third row. So this means that we are removing third row. So from this one we would get 0 0 1 0, and this one also we would get 0 0 1 0. So when you think of this as a set, we don't in a set there are no repetitions, right? So we only keep like one of them. Yeah. So this is X minus 3. Okay. So if this is X, if this is the set X, this is the set X minus 3. This is okay. This should be a curly brace because this is a set. This should be a curly brace. This is also a set. So now I can like define this projection onto like even not just one row, multiple rows at once. So for example, I can define XS to be X minus S, where X is an X, and S is a subset of the rows. So this just means that you take the rows indexed by this set S and then remove it. So for example, if I take S to be 2 comma 3, sorry, that's a bad, what is X minus 2 comma 3? So these are all the matrices that I get by removing the second row and the third row. And what is this set? It's just a singleton set, right? If I remove the second row and the third row, there's only one kind of pattern that appears, that's 0, 0. So these are all partial matrices with just one row. So this is some notation. So far we haven't done anything. This is some notation that is going to be very useful. So are there any questions about this definition? Okay, if not, let me continue. So now with all these definitions, we can define the information measured. So we said we are trying to measure the information and this set X. This is a set of matrices. So some set Xi, some, I don't know, some set Xi of matrices. So maybe not Xi. I don't know, just some set of matrices X. So we view this set as a bipartite graph. So what are the two parts? So on the one part I have x minus 1 and the other part I have x1. So what is x? So there's some more notation. So what is x1? X1 is like the projection of x onto the first row. So it's like, so in this notation I could sorry, this should be x minus s. So in this notation I meant, if I put a minus sign, it means that we are removing everything, every row that is indexed by s. And you can define a similar thing where like you can define xs to be projection onto the set s where we keep all the rows indexed by s. So minus, so basically just to clarify, so x minus s means remove all rows indexed by s, and xs is keep only the rows indexed by x, or rather it would be like remove s complement. Yeah, so if I define minus s to be the complement of s, it's just projection of x onto the rows indexed by complement of s, right? If I define minus 3 to be the set, so the universe here is the set of rows, which is m, which is 1 2 3. It's a set 1 2 3 minus 3, right? So then x minus 3 is just x projected onto, this is equal to x projected onto 1 2. So just some more notation just to make our lives easy. So if you see x minus s, that means remove the rows indexed by s, and if you see xs, that means keep only the rows that are indexed by s. Yeah. So then what is x minus 1 and x1? So for example, in the exam, for the concrete example that we took here, so let me just copy that over. Oops. This visualization is going to be this following. So this is our set x. Yeah, set x, and we visualize this set x as like two parts, which is x minus 1 and x1. And we already so what is x minus 1? We did not do x minus 1. So x minus 1 is all the matrices where the first row is removed, and how many different patterns are there. From the first matrix we get 1 1 0 1, so we get this one, and the second one we get 1 0 1 1, right? And the third one we get 1 0 1 0. So it seemed like no two different matrices gave the same pattern, but we saw that in some cases two different matrices can give the same pattern when you project out a row. So this is x minus 1, and what is x1? So let me put this in the graph as well. So x minus 1 had 1 1 0 1, and then 1 0 1 1, and here we had 1 0 1 0. And what is x1? So this means, so whenever you see a positive sign, that means keep only that row or that set of rows. Here this is one row. So what is x1? So that is, there's no variety there, right? That's just this partial matrix 0 0. So if you think about, so this set can be visualized as this bipartite graph. On one side you have the partial matrices where the first row is removed, and the other side we have the partial matrices where only the first row is kept. And what is the edge? So so far we have described the vertices of this bipartite graph, and now we describe the edges of this bipartite graph, and the edges are going to be, so let me choose a different color. So there's an edge between two things if the completed matrix, so here is a partial matrix where the first row is missing, and here is a partial matrix which is only the first row. So if you put them together, how do you put them together? So you put 0 0 on the top and 1 1 0 0 on the beginning, and if that matrix is in the set X, then we put an edge between them. So in this case it so happens that there's an edge, there are all possible edges. But in more interesting examples, maybe like it's not a complete bipartite graph and there's an edge only if the partial matrices, the complete matrix that you get by putting the left hand side and the right hand side together in the proper way is in the set X. Okay, are there any questions about this representation? So here, so we there's nothing to do with the protocols. We have some set of matrices and we want to visualize them as this bipartite graph. So what is our goal? We want to understand how much information the players have learned about a particular row, right? So we want, so this way we are, so on the one side we have everything but that row, and the other side we have that specific row. So we're going to use this graph to figure out how much information that they know. Okay, so here I did it for x minus 1 and x1 in general. So let's define this graph. So given this, oops, that's a bad color. So given this set, the subset of matrices, these are m by n matrices, we can define gi, the ith graph, to be, so this graph would tell us how much information is there in the ith row. So gi is this bipartite graph. On one side we have matrices from x where the ith row is dropped, so this is x minus I. So these are all like, these are matrices of this kind of form where this row is missing. So this is a node here, and on the other side we have xi where we have only the ith row. So we put a edge or a, like, we put an edge between them if this completed thing is in the set X. Okay, so maybe if you complete it this way, so maybe this is like 0 1 0 or something, maybe 1 1 1, you don't get an element. If you put that thing here, you don't get a matrix in the original set, so maybe in that case you don't have an edge, and things like that. So this is the graph. So given this set of matrices X, for every I, so what is the I? I is a row, so for every I in an M, so there are M rows, so for every row we can define this graph, right? And now we define this measure, which is the average degree of this graph I, of average degree of gi, but it's the left average degree. So this is the average degree of a node in the left partition. So if you have seen some graph theory, so average degree is like the, so for every left node there are a bunch of neighbors. On average, how many neighbors are there? So an equivalent way to define this would be, what is average degree of a node on the left hand side? It's the number of edges divided by the number of vertices on the left hand side. What's the number of edges? So this is the number of total edges edges in GI divided by number of vertices on the left side. So this is the left average degree. So this thing is clear, right? So number of vertices on left side is just cardinality of this set x minus I. These are all set of matrices that you get by projecting out the ith row, and if you get the same matrix from two different matrices by removing the ith row, you only keep one thing because it's a set. So this is cardinality of x minus I. And can someone tell me what is going to be the total number of edges in GI? Any guesses? So the way we constructed this graph, we put an edge between two vertices only if the completed matrix belong to X. So there will be one edge for every matrix in X. So the top thing is nothing but cardinality of X. Yeah. So I can, so this is going to be my information measure. So the definition is that average degree, so the ith average degree of this set X. So remember that set X is a set of matrices, m by n matrices, and this average degree, the ith, is like, it's the cardinality of X divided by cardinality of x minus I. So let's try to make sense of this definition of information. Oh, by the way, the predictability measure that the original paper of EIRS uses is just inverse of this because they are measuring information. So just to tie up things, I'll define. So similarly, so for any, just this quantification is clear to you. So for any subset of matrices on m rows and n columns, and for any row I which is in m, this is defined, and similarly define predictability at the ith row for this set of matrices X to be 1 over the average degree. Yeah. Okay. Now let's try to make sense of this measure of information. Okay. By considering some examples. But before we do that, are there any questions about these definitions? This should be a good time. So we're getting. So this is the main thing. So once we define this measure, we just need to like show some properties of this measure, and then we are pretty much done with the cleanup. Okay. Okay. If not, let me move on. So the first example that I want to think about it is like, okay, so we have this set X. So some examples X, to make sense of this measure. So the first set X is X where all this, it's the subset of 0 1 to the m cross n, where first row is all zeros, 0 to 10. So these are all set of matrices where the first row is all zeros. So if you think about it, then the amount of information in the first row is like almost full, right? So they know entirely what the first row is. So what Alice and Bob did, they did some communication and figured out that the first row of all the matrices that they have is all zeros. So in this case, there's no amount of uncertainty left to learn about the first row, or rather the amount of information in the first row is the maximum possible. So hopefully the definition of information that we came up with should be able to capture this situation. So what's going to be the graph here for, so we want to know what is average degree of the first row in this particular example X. So what's the example X is going to be? It's something like this, right? In this particular example of our set, we did in fact, it was this exact, yeah, I didn't plan this, but it so happened that we ended up with all the matrices whose first rows was 0, all zeros, right? So it's the graph x1, sorry, this should be x. So the graph, so the average degree 1 of this set x. What is this set? So it's the average degree of the nodes on the left hand side. So what is the degree of any node on the left hand side? It's exactly 1, because they have figured out the first row is all zeros. Then there is only one way to fill that row, so that is just 1, right? So the average degree, max degree, min degree, all of them are 1. So but if you go by the definition, how many edges are there? So this should be cardinality of x divided by cardinality of x minus 1, right? So how many edges are there? There are 3 edges. And how many vertices are there on the left? 3. So this is 1. But you might think that that's like telling this one bit of information, but information is always defined to be logarithm of something. So logarithm of the average degree is the amount of information that is not known in the matrix. And what is that? Logarithm of 1 over 1 is, or 1 is just 0. So it's like 0 amount of information that we need to learn about the first row. Yeah. So in this particular example, the average degree of 1 of x in this more general example is just 1. So the information, so the amount of information left to learn about first row is this logarithm of this 1 over the average degree. So this is like log 1 over 1 and 0. So there's like no amount of information that is left. And this should be the case, right? Because they know what that is completely. Yeah. So in this situation, our information works very well. So this is example 2. So this is the case I was sort of alluding in the beginning of this definition. So we have a set of matrices X such that they know that the parities, if you take any matrix in the set X and you take the parities of any column, that's going to be 0. So they know that all the so this is all the set of binary matrices, mi and matrices, where if you take the parity of any single column, it's going to be 0. So for example, like if you take some concrete example, if you take m equal to 3 and n equal to 2 or something, then so this set is going to be, what is this going to be like? You have, so the first, so there are 3 columns and 2 rows. So you can fill in any 2 rows to be anything. You can fill in any 2 rows to be anything, but in this, for the resulting matrix to be in the set, the parity of every column has to be 0. So the last column is already decided. So this parity has to be 0. So this has to be fixed to 1, and this has to be fixed to 1 as well, right? So it's all matrices of this kind. So if you think about it, and so if I fill in, let's say 1 1 1 1, I can fill in for any 2 rows, and then I the third row is completely decided here, right? So if you fill in 1 1 1 1, this has to be 0 0, because the parity already is 0, so this has to be 0. The parity already here is 0, this has to be 0. Yeah, and just, but it doesn't matter which 2 rows you fill in, the third row is defined. So for example, if I fill in 1 0 0 1, for this matrix to be eligible to be in this set X, then I need to fill in here 1 and 1 here as well, right? So these are not all the set of matrices, but like there's a set of matrices. If you tell me the m minus all but 1 row, I can figure out what the last row is. So if you tell me the rows from 1 to m minus 1, I can figure out what's the last row. Or if you tell me the rows from 2 to m, I know the first row. Yeah. So is this set clear? So the set X is so all X such that parity of every column is 0. Okay. So here it seems like they don't really know about one. So this was something I was trying to explain in the beginning. Maybe it was not so clear back then. So this somewhere where we don't know which row they really know about, because if you give me any set of rows except one row, then I know the other row that you have given me. But in this case, we can at least fix some row and then say that that row is completely known, right? So what is the average degree I of I in X in this particular set X? So no matter what that I is, what is X minus I in X? This graph is going to look like the following. So in X minus I and Xi we have here. So what is it going to be? So for example, if we take the example here, let's say I is, so for example, let's first try to figure out what is x minus 2 and x minus, so x minus 2 and x2. So these are all the matrices where the second, on the left hand side we have matrices or where the second row is deleted. So for example, so this is the first row, this is the third row. So let me fill in 0 1 1 0. How many neighbors can it have? It has only one neighbor, right? So this node is only connected to one particular neighbor, and that neighbor should have parities to, so that the column parities become 0. So this is only one neighbor, and on the right hand left hand side I have all possible m by n matrices, right? I mean, sorry, m minus 1 by n matrices, but it doesn't matter, every one of them have degree 1. So the average degree of in x minus 2 x2 is just 1, and it didn't matter if you remove the second row, first row, the third row, or no matter what other row. So it says that average degree I of x for any I is going to be 1. So if you think about the amount, so now you translate to information, the logarithm of 1 over 1 is 0. So this tells you that the amount of information that the players know about the ith row given every other row is 0. Sorry, it's full. So there's no amount of uncertainty left if you give me all the rows but one row, right? So this also, so we, as an adversary, now we can choose which row, which row to blame, and we can say, okay, so in this kind of precarious situation where we don't know which row is row is responsible for leaking information, we'll pick one of them arbitrarily, and then by our definition of information it says that, okay, no matter what row that you pick, there's no information left to learn about that row, because no matter what I you picks, the average degree of x minus I onto xi is just 1. Okay. And what happens in the, so what the example 3 is just the other extreme. It's where the set X is all the possible m by n matrices. So in which case, what is the average degree like? So on x minus I, so if you take any matrix where the ith row is removed, since you are allowed in the set X, you are allowed all possible binary matrices. What is the degree of a particular x minus I here? So if you take a particular x minus I, how many neighbors xi would be there? These are going to be all possible neighbors, right? Because we have the set of all possible binary matrices on m rows and n columns, we can fill in the ith row in whatever we want. And how many possible ways are there to fill in the ith row? In the ith row there are n bits, right? So if you think the matrix was something like this, so there are like m rows and there are n columns. So in the ith row in particular there are n bits. So the degree of every node here is what? It's 2 to the n. Yeah. right? So the amount of information left to learn about these rows is, so what's the average degree? So for any I, average degree I of this particular set X is exactly 2 to the n, because every node has degree 2 to the n, so average will also be 2 to the n. Or you could just do the calculation. So what is cardinality X? It's all m by n matrices, so that's 2 to the mn. And what's cardinality X minus I? It's all m by n matrices where the ith row is removed, so it's all m minus 1 by n matrices, so it's just 2 to the mn minus m, which is, sorry, mn minus n. So there are so there are m minus 1 rows and n columns, right? So this is 2 to the n by a different calculation. So in this case, what's the amount of information? Amount of information left to learn about ith row. So that's logarithm of the average degree, which is log 2 to the n. That's n bits. That's a maximum amount of information, and this is consistent with what we know, right? They haven't ruled out any matrix from the set of matrices, so they don't know nothing about any row. So this also says that, okay, yeah, the amount of bits left to learn in any row is n bits. So so hopefully with these examples, it's sort of clear that this may be a good definition of information. And yes, we want to like the second thing that we want to ensure is that under this definition of information, we have to say that if m bits were revealed on a matrix, there are at most m by tau revealed rows, where tau is the threshold that we choose. So sort of this information gets spread out. So to before we actually prove that, let me show you with one example. This is sort of intuitively true, and then in the next class we'll prove these properties and complete the cleanup, and then we'll do the second stage and tie it up. So the final example is just going to be this example 2. So in this example 2, if you think about it, it says that, so here there's only like one. So how much amount of information has been revealed on this set? So this set, so intuitively the amount of information info revealed, can someone take a guess? So we know that parity of every column is 0. So the amount of information revealed is exactly n, right? So there are like n bits of information that we know. So there are n columns, 1 to n. So this is n bits. And we want to say that this n bits can be attributed to some row. Okay. So how do we do that? So now, so here is an example. So in the example number 2, we had this set X. So I'm going to take like 3 more minutes. I know I'm like over time by 20 seconds. So I'll take 3 more minutes and wrap it up. And if you have to go, you can go. I'll upload it. I'll upload all the previous lectures like tomorrow. So yeah, I'm going to take 3-4 minutes. So this set X was this subset of 0, 1 to the m cross n, where parity of every single column was 0. And now we sort of saw that the amount of the information that is revealed into this matrix can be attributed to any row. So I claim, like, let's take this to be the first revealed row. We say that the first row is a revealed row. So because average degree of x minus x, average degree 1 at x is 1. So there's no information left to learn, so it's a bad row. We want to like remove that row from the picture. So what are we going to do? I'm going to say that if you fix that row as the function of the remaining rows, then the amount of information in the remaining matrix, in remaining partial matrix, is like almost 0. There should be like all the amount of all the information that the players have learned about this matrix can be attributed to row 1. I mean, in fact, it can be attributed to any particular row, but I'm going to choose row 1. So how are we going to show that? So we take this graph x minus 1 and x1, right? So we know that every matrix here has every partial matrix here has exactly one matrix on one row on the right that it completes to. So we know that, okay, and this row there's quite a lot of information revealed, so we're going to remove that row from the picture. So what do I mean by that? Just like fix that. So it's only one choice, right? For every left node in the graph, I'd mentally keep one of the nodes on the right as the match. But in this extreme example, there's only one of them. But in the case in future, there would be like, maybe we would consider sets where there are like more nodes on the right, but we'll choose one of them. So once we have fixed that, the set of matrices X is really defined by X minus 1, right? Because from X minus 1, there's a 1 to 1 correspond to X1. So we just need to think about X minus 1. So in this case, in the set X minus 1, are there any more rows where they have learned a lot of information? And how do we check for amount of information in a particular row? We look at the average degree. So for example, so what is X minus 1? So it's all set of all matrices from X where you remove the first row, right? You keep all the rows 2 to M and you remove the first row. So this is this set obtained from X. So I want to claim that in X minus 1, there are no more revealed rows. This is consistent with our intuition, right? The set X said that, okay, if you tell me all the rows 2 to M, I know the first row. So we have already said that, okay, that is correct. And the first row, you have learned quite a lot of information, but we have removed the first row. We have fixed the first row as the function of everything else. In that case, we want to say that there's no information left in the remaining rows, and this should be by intuition, this should be true, and by our definition also it would be true. Why? So how do we check for information in the remaining rows? Let's look at average degree 3 of this set X minus 1, right? So this is a set minus 1 by, so how do we define this average degree 3? So this is basically like, you take this set X minus 1 and from that you remove the third row. So this is on the left hand side, you will have every matrix from X where the first row and the third row is removed, and on the right hand side you just have like all the for all the matrices in X minus 1, take only the third row. Yeah, so it's similar. Like, if we had defined these things for a general set of matrices, X minus 1 minus 3 and X minus 1 3 are very clear, right? So from this, so this set X minus 1 is sort of as the current set of matrices. They are partial matrices, but that's fine. Matrices, and from that set of matrices you remove row 3 and keep it on the left hand side. On the right hand side you have 3. So what's average degree here? So on this set, what is set X minus 1? So if you think about it, set X minus 1 is indeed the set of all m minus 1 by n matrices. So you can fill in whatever values here because there's no restriction, right? So only restriction on the set X was that all the parities of every column should be 0, but that you can fix by choosing the first row, and we have chosen the first row in a way that that constraint is matched. So once that constraint is removed by removing the first row, there's no constraint, so the X minus 1 is just 2 to the m minus 1 times n. So and what is X minus 1 minus 3? Just 2 to the m minus 2 times n. So the cardinality of this set is 2 to the m minus 2 times n. And what's the average degree? So that is just 2 to the m minus 1 times n divided by the m minus 2 times n, which is just 2 to the n. And so the amount of information left to learn about the row 3 is just n bits, so it's maximum. Yeah. So this gives you this spreadness condition as well. So if you classify some row as so if some row has very low average degree and you fix that row as a function of the other rows, the remaining the set of in the remaining set of rows, uh, that you've accounted for that much information outside the remaining set of rows. So if there was one row which has all the information, then in the remaining set of rows there's no information left. So this intuitively shows the spreadness property, and in the next lecture we would prove it formally using an algorithm. So I think I'll stop here and I'll hang around if you have any questions.